Okay. Then today, what we are going to work on is we're actually going to kind of work our way to the last couple. So there's homework due on the 5th. So the 5th is the Monday. So homework is due on Monday mornings. So there's homework due on the 5th. Those 3 sections that are due on the 5th. So today what we're going to work on is there are basically 3 tests that we have yet to do in terms of series tests. And so we're going to cover those 3 tests today. That's not the end of series, so we're going to be doing more stuff with the tests and more stuff with series, and actually probably more useful / interesting sort of stuff with series after spring break. But we're going to finish, hopefully, the basic tests today. So the first thing we're going to do is section 11.7, which is the ratio and root tests. Okay, so we're going to start with the ratio test. And what the ratio test does is the ratio test basically extends the geometric series. So it's based off of the geometric series test. So it extends the geometric series test by looking at ratios. And so what the test says is let the summation of a sub n be a series with positive terms. Then we're going to look at the limit as n approaches infinity of the absolute value of a sub n plus 1, so the a sub n plus first term, divided by the a sub nth term, and basically one of 3 things is going to happen. So if you remember the geometric series, we were always comparing to it, is it less than 1 or is it greater than 1? So similarly, we're going to have a less than 1 case, a greater than 1 case, and then we're also going to have an equal to 1 case. So just like the geometric series, if it's less than 1, it converges. So same thing here. So if this limit turns out to be less than 1, it's going to converge. If it turns out to be greater than 1, it's going to diverge. And if it's equal to 1, tough luck. You have to do another series. It's not that you did anything wrong. It's just that this test isn't going to help you figure out what's happening to the series. So those are the 3 things that could happen. Questions? No? Okay, so before we go into actually working out the series, I want to kind of go back to factorials for a minute and have us think. Correct. You divide one of the terms of the series by the previous term in the series. Yep. So you're looking at the ratio of those 2 terms. So ratio test is used a lot when you have a factorial. And the reason it's used a lot when you have a factorial in your series, so in particular, if I have a series and it's like, does the series converge or diverge, and it has a factorial in it, the first thing I think about doing is the ratio test. And the reason why is because this division, this ratio of a sub n plus 1 over a sub n, will actually cancel out factorials that I have. So let's talk about factorials here for a minute. So I think like when I first did factorials, we talked about 7 factorial, right? So 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, right? That's what the factorial means. Start at that number, go down in whole number intervals all the way down. The thing to notice, though, is that 6 times 5 times 4 times 3 times 2 times 1, well, that's actually 6 factorial. So another way to write 7 factorial is you could write it as 7 times 6 factorial. Another way to write it, so if I looked, here I have 5 times 4 times 3 times 2 times 1. That's 5 factorial. So I could write this as 7 times 6 times 5 factorial. So the idea is you can kind of peel pieces of the factorial off and just keep them around as multiplying. Same thing, I could keep this as 7 times 6 times 5 times 4 factorial. And we're going to use this idea, but we're not going to use it so much with an actual number factorial. We're going to use it with things that maybe look like n plus 1 factorial. So why are factorials important? It's kind of a shorthand notation. So a couple reasons. So it's kind of the factorial itself is just a shorthand notation for us in math when you have a bunch of numbers and you're multiplying them all together. The factorials actually come into play in series and sequences for us when we get to power series and Taylor series and Maclaurin series, and those series are used to represent functions. And so you need these things because they come from derivatives. And if you think about it, if you think about x to the 7th, right? So I'll kind of put it over here. If you think about it, if you took x to the 7th and you took the derivative of x to the 7th, that would be 7x to the 6th. And then if you took the derivative of that, right? So the derivative of 7x to the 6th would be 7 times 6x to the 5th. So the factorials kind of come in from are naturally generated as you keep taking more and more derivatives of power functions. And so that's why they're actually become, so it's like a nice way to write the derivative in a closed form, basically. Yeah, it is pretty cool. No problem. So just like I peeled off pieces here, right? I could take off the 7 and then say it's 7 times 6 factorial. You can do the same thing when you have something like, say, n plus 1 factorial. That's going to be n plus 1 times n factorial, right? So I can take the first term off, and then if I subtracted 1, n plus 1 minus 1 would give me n factorial, right? Or you could even think of it, it's n plus 1 times n times n minus 1 factorial, right? So I could pull off the first two pieces. Just like over here, I pulled off the numbers. I pulled off the 7, and then I pulled off the 7 and the 6, and then the 5 factorial. So you can do the same thing even if they're not concrete numbers, but they're representing, right? And n plus 1 is representing some number. We just don't know what it is. And so we're going to use this type of argument a lot today. So questions about any of that before we go to a problem where we're actually going to use it. No. Okay. So, determine if the following series or not sequences. Following series converge or diverge. So A, the summation n equals 0 to infinity of 2 to the n over n factorial. So again, I kind of already gave this hint, but if your problem has a factorial in it, you're almost always going to use the ratio test. It's not 100% you're always going to use it, but pretty close. So if I have a factorial in it, that's the first thing I try. So we're going to look at the limit. So we're going to do the ratio test. And we're going to look at the limit as n approaches infinity. And I should have kind of moved this down here a little bit. Okay, so limit as n approaches infinity of, okay, so a sub n plus 1. So a sub n plus 1 means everywhere you see an n, instead of an n, you're going to put n plus 1. So it's 2 to the n plus 1 over n plus 1 factorial, all divided by a sub n. So 2 to the n over n factorial. Questions on how I got that? No. Okay. So first off, all of my terms there are positive. Everything I have there is positive. So I'm going to drop the absolute value sign. If you weren't sure if something was positive, then you would need to keep the absolute value sign. And the absolute value part is going to become important in a couple sections from now. So we're looking at the limit as n approaches infinity of, so my top fraction is 2 to the n plus 1 over n plus 1 factorial times, right? So change the multiplication, flip the bottom fraction, n factorial over 2 to the n. Okay, so now, hopefully some stuff cancels out for us, right? Because if you tried to put in infinity right now, you're just going to get infinity over infinity. And I don't know how to do L'Hopital's rule when there's a factorial, because I don't know how to take the derivative of factorial. So to be able to hopefully figure out this limit, hopefully some stuff's going to cancel out. So if I look, remember this n plus 1 factorial, we just talked about how this is really n plus 1 times n factorial. So this n factorial cancels with that n factorial. We also have a 2 to the n and a 2 to the n plus 1. So the thing to remember is when you have 2 to the n plus 1, that's really saying you have 2 to the n times 2 to the first. So the 2 to the n parts cancel each other out. And what I'm looking at here is the limit as n approaches infinity. So left on the top, I have a 2. On the bottom, I have an n plus 1. So we're looking at 2 over n plus 1. And if you plug infinity into that, it's going to end up being 2 over infinity, which goes to 0. And 0 is in fact less than 1, so this is going to converge. Questions? No? It's not too terrible yet, right? When I say that, people are always like, yeah, yet. Like, what's coming? I actually don't think. I like the ratio and the root tests. Or, well, we haven't gotten to the root test, but I like them. Okay, David, yes. Go for your question. Okay, so how I cancel the n factorial. So remember, it's kind of like this. Like if I had, so let's think of it with numbers for a second. So let's say I had 7 factorial and over here I had 6 factorial, right? So remember, 7 factorial is really 7 times 6 times 5 times 4 times 3 times 2 times 1. So this 6 times 5 times 4 times 3 times 2 times 1 is 6 factorial. So this 7 factorial I can rewrite as 7 times 6 factorial, and then the 6 factorials will cancel each other out. So does it make sense in terms of numbers? So let's start there. Okay, so I did the same thing. It's just that I don't have concrete numbers. However, I had n plus 1 factorial. So just like I peeled off here the 7, I took 7 and then 7 minus 1 is 6. So 7 factorial is 7 times 6 factorial. I can do the same thing here. I have n plus 1 factorial. So I'm going to peel off the first thing, which is n plus 1. And then I have to think about taking n plus 1 and subtracting 1. So if you have n plus 1 minus 1, that gives you n. So what you're left with next to it is n factorial. And then this n factorial here cancels with the n factorial here. No problem. Any other questions? It's weird the first couple times you see it. But it's used, this idea is used a lot in the ratio and the root test, or in the ratio test, I should say. So you get used to it eventually. Okay, let's look at another one. I'll go to there, but okay, B, the summation n equals 0 to infinity of n squared 2 to the n plus 1 divided by 3 to the n. Okay, so again, you could begin to go through all the tests that we have, right? So if you did the divergence test, right, this is not going to work out. If you do, it's not a geometric series, it's not a P series. I don't really want to integrate that, so it's not going to be an integral test. We did last time the comparison test, and so you might be able to take this and do the comparison test. But this problem is actually a pretty good candidate for the ratio test. The other time I like to use the ratio test is if you have a bunch of stuff that's multiplied and divided, which we do, and it kind of is all different stuff, right? So I have like 2 to a power n, I have 3 to a power n, but then I also have this n squared, so I have kind of a lot of stuff going on. So if that's the case, then the ratio test is actually a good candidate of a test to use for that as well. So use the ratio test. So ratio test. So we're going to look at the limit as n approaches infinity. Okay, so again, n plus 1, which means everywhere I see an n, I have to replace that n with an n plus 1. So it's going to be n plus 1 squared, 2 n plus 1 plus 1 over 3 to the n plus 1. So that's the a sub n term, and then that's all going to be divided by n squared 2 to the n plus 1 over 3 to the n. Questions about how I got either one of those terms? I'm always self-conscious teaching on Zoom, and like when I need to take a drink. Like in the classroom, like I have no problem taking a drink, but I feel like you're not like, inches away from my face. Whereas here, I feel like I take a drink and, you can all like watch me swallow and like hear me. So I know. Yeah, but then I'm like, oh, but if I don't drink, I'm going to start coughing. So I'm like, because my throat gets dry and stuff. So it's just so bad. Like, we need to just be back in the classroom. I'm not a fan of this whole Zoom experience. Oh, I could see that. Because you're like so close. Like, yeah. I don't like it. All right. I also say these little things to try to give you guys time to kind of catch up with me and stuff like that. So nobody's asked me about where this came from. So if you do have a question, definitely say it. Okay, so again, all of these pieces are positive, so I'm going to drop the absolute values. And the other thing is I'm going to do the keep change flip, right, on the fractions. So this is going to become the limit as n approaches infinity of n plus 1 squared, 2 to the... Okay, so on the top, we could put those together, right? So I have n plus 1 plus another one. So this is 2 to the n plus 2 over 3 to the n plus 1 times 3 to the n over n squared 2 to the n plus 1. Does that make sense? Yes. Okay. So now I can cancel stuff out, right? So 3 to the n is going to cancel out the n part here, right? And I'm just going to be left with 3 to the first. Kind of just, that's my shortcut way of writing it, but really remember you can think of this as 3 to the n times 3 to the first. So the 3 to the n part is canceling out. I just usually cancel out the little exponent, the n part. 2 to the n plus 1. All of these would cancel out here, and I'd just be left with 1 left over, right? And again, that's because this is, you could write that as 2 to the n plus 1 like I had it up above. So the 2 to the n plus 1 part cancels. And then I can't cancel the n squared part. So this is going to be the limit as n approaches infinity of 2 times n plus 1 squared over 3n squared. Or, if I multiplied this out, right, we'd have the limit as n approaches infinity of 2 times n squared plus 2n plus 1 all over 3n squared. Or the limit as n approaches infinity of 2n squared plus 4n plus 2 all over 3n squared. Now, a couple ways you could do this limit. One of the ways you could do the limit is you could plug in, so you get infinity over infinity, do L'Hopital's rule twice. One other way you could do the limit is you could divide everything by the highest power in the denominator. So divide everything by n squared, and then you'll see you get 2/3. The other way to do it is just remember from Math 126, we're basically finding a horizontal asymptote of that function. And so since the degree on the top and the degree on the bottom is the same, the highest power on the top and the highest power on the bottom are the same, I could just take the ratio of the coefficients. So this whole entire limit just turns out to be 2/3. And again, multiple ways you could do it. I don't care which way you do it. So if you are like, oh, I totally would have done L'Hopital's rule, right? Great, do L'Hopital's rule. If you did that, you would have to do L'Hopital's rule twice, right? So you get the limit n approaches infinity, 4n plus 4 over 6n squared. That's still infinity over infinity. Do L'Hopital's rule again. You'd have 4 over, oops, not 6n squared, just 6n, right? I took the derivative wrong there. I'm like, wait a minute, something's not adding up here. 6n. So you'd have 4 over 6, which is in fact 2/3, right? So you can totally do L'Hopital's rule to find the limit. I personally, on my paper, I went from this step here to the limit as 2/3 because I could recognize, oh, on the top, I have an n squared. Oh, my cursor froze. It's not good. See if it catches up with us here. So on the top I have an n squared, and on the bottom I have an n squared. So I knew the power on the top was the same as the power on the bottom, and so the two would, those powers of, like, they're same power of n, so it's just going to be the ratio of the coefficients. And just to finish up the problem, we'll see how laggy it is. 2/3, right, is less than 1, so it's going to converge. Questions? No. All right. So let's try another one then. So let's try part C. So the summation n equals 1 to infinity of n to the n over n factorial. Okay, so again, I see a factorial. I'm going to try the ratio test. So we're going to look at the limit as n approaches infinity. Okay, so this is going to be the absolute value of n plus 1 to the n plus 1 over n plus 1 factorial divided by n to the n over n factorial. Questions? Okay, so again, we're going to do same thing. All of that stuff is positive, so we're going to do keep, change, flip. So I've got the limit as n approaches infinity of n plus 1 to the n plus 1 over n plus 1 factorial times n factorial divided by n to the n. Oh, I don't think I can hear. Yeah, Oh, you're right. Mine are muted. Okay, wait a minute. Well, yes, totally right. Give me 1 second here. I lost my... Okay. Close that. Okay, now I'm not muted. So I'm going to assume that Delta must have tried to actually ask me the question out loud, and then I didn't hear you. So then I was just, yes, I can go over how I got it. Right. So make sure I can actually. Okay. All right. So were you asking how I got this top part here? Okay, yeah. So basically what I do is, remember that the top is a sub n plus 1. The bottom's a sub n, right? So what you're given, when you're given this, they're telling you that is a sub n. So I'm going to come over here. So we have that a sub n is n to the n over n factorial. And so what we're doing to get a sub n plus 1 is everywhere I see an n, I'm replacing it with n plus 1. So this n here now needs to become an n plus 1. This n up here now needs to become an n plus 1. this n on the factorial needs to become an n plus 1. So that's how I got n plus 1 to the n plus 1 divided by n plus 1 factorial. Does that help?
Yeah, thank you. That clears it up a lot.
No problem. Sorry I couldn't hear you.
That's okay.
Other questions? You guys have been able to hear me the whole time, right? Like, even though I couldn't hear you, you could hear me, right, talking? Okay. All right. I figured if you couldn't hear me talking and I started, like, writing, like, somebody would say something, but you never know, so. Okay, other questions before we keep working this out? No. Okay. So the n plus 1 factorial, right? Remember we've talked about this. This is n plus 1 times n factorial. So the n factorial is going to cancel with the n factorial there. And so what we really have so far is the limit as n approaches infinity of n plus 1 to the n plus 1 over n plus 1 times 1 over n to the n. And if you notice, I have an n plus 1 on the top and an n plus 1 on the bottom. So I actually could cancel those powers a little bit. So this n plus 1 cancels out the plus 1 part there, because it's canceling out one of the n plus 1s. So we're left with the limit as n approaches infinity of n plus 1 to the n all over n to the n. And so if you try to plug in, you end up with infinity over infinity, which is fine, okay? Do L'Hopital's rule. The problem is when you go to do L'Hopital's rule, you have to take the derivative of n to the n, or n plus 1 to the n. So remember, that would be like taking the derivative of x to the x. So if you had me for Calc 1, which I don't think there's many people here who did have me for Calc 1, but like in my Calc 1 class, we figure that out. We figure out what x to the x is. But to take the derivative of x to the x, you have to do logarithmic differentiation. So the idea is like, I don't really want to have to do logarithmic differentiation just on the top and logarithmic differentiation on the bottom to hope this stuff cancels out to be able to find this limit. So we haven't really used them, but back when we did, I think when we did just sequences, on the day we did sequences, we talked about some different commonly occurring limits. So if you remember, I put up 6 of them and I said, hey, if you have these limits, you're just free to use them. You probably want to have them handy, like as you begin to go through and do the homework, like kind of from this point forward, because you might end up needing to use some of those limits. And so one of those limits on the sheet is actually going to be helpful for us here. But we have to do a little bit of work to make it work for us. So the first thing I'm going to do is I'm going to notice the top is raised to the n power and the bottom is raised to the n power. So I could actually rewrite this as the limit as n approaches infinity of n plus 1 over n all to the nth power. So basically I took the nth power that was on the top, and since the bottom was also raised to the n, I just made it that whole fraction raised to the n. And then I can actually divide this and make this the limit as n approaches infinity of n over n plus 1 over n all to the n. And so this becomes the limit as n approaches infinity of 1 plus 1 over n to the n. And that actually looks somewhat similar to one of the limits that I gave you in those commonly occurring limits. So in that list of commonly occurring limits, I'm going to write it here. Number 5 was the limit as n approaches infinity of 1 plus x over n to the n turns out to be e to the x. So what's the only difference between my limit and that commonly occurring limit? What I wrote in pink. Yeah, so the pink limit has an x instead of a 1, where ours has a 1. And so instead of our final answer going to be e to the x, since we don't have an x, we have a 1, it's going to just be e to the first. So it's using that commonly occurring limit, but we happen to know what the value of x is for us. It's 1. So we get e to the first. And e to the first is something that's bigger than 1, so this sequence is going to diverge. Questions? So once in a while, you might need to use one of those limits. So if you get to something you're like, I don't know, try looking at those limits or have those limits close by because they might come in handy. So that's basically the ratio test. So the ratio test is actually going to become really important a couple sections from now. So a couple sections from now, we're going to actually talk about what's called the radius and interval of convergence. And so the idea is we're going to be given a series that actually has x in it, and we want to figure out, well, for what values of x would this series end up converging, or for what values would it end up diverging. And to do that, we're going to use the ratio and the root test. So mostly the ratio test. So the ratio test actually does become important. Right this second, it's kind of like, okay, it's just another test. But you're going to see that we actually end up using the ratio test a fair amount. Okay. It's kind of similar to the ratio test. So the root test says, let the summation of the a sub n's be a series with a sub n greater than or equal to 0 for n bigger than or equal to n. So I probably should have written the ratio test that way too. So again, the reason we say the positive terms, we're talking about far enough out, everything gets positive. So that's all this is saying. Far enough out, everything gets positive. And this time we're going to look at the limit as n approaches infinity of the nth root of the absolute value of a sub n. And again, it could end up being less than 1, equal to the 1, or greater than 1. And just like before, if it's less than 1, it converges. If it's equal to 1, tough luck. That's a pretty... My face is like... It's like it's turned sideways and sad. Right? I think I'm just going to leave my sad face like that. And then finally, if it's greater than 1, it diverges. I feel like my sad face is almost like looking at the tough luck, being like, what? Tough luck? Ugh. So, giving it a little bit of personality here. I was about to say this morning, but this afternoon. It did. Ooh, it lived through 2020, right? I mean, think about it. It's kind of crazy, right? We're living through a pandemic, so, you know, the last time there was a pandemic, right, was like 100 years ago. So it's kind of, you know, hopefully, fingers crossed, that's a once in a lifetime thing. Right? Hopefully there's not another pandemic in my lifetime, but we'll see. Hopefully not. All right. So, the root test, the ratio test is used way more than the root test. So the root test, you have to be able to use the root test, you kind of only want to use it when your series has stuff raised to the power n. And so even sometimes, like, because if you go back and you look here, like we had, you know, part C had something raised to the power n. Part B had something raised to the power n. Part A had something raised to the power n. So a lot of times, even though you have something raised to the power n, that's not just saying, oh, use the root test. The root test I mostly only use when everything in my problem is raised to the is being raised to the power n. So I'm going to just put that as a little side note. So usually only used when all the pieces of the series are raised to the power n. Okay, so for example, determine if the following converge or diverge. A. The summation n equals 1 to infinity of e to the 2n divided by n to the n. So, everything here is has an n in its power, right? The e to the 2n, there's an n in the power. The n to the n, there's an n in the power. So, we are going to use the root test. So we're going to look at the limit, n approaches infinity, of the nth root of e to the 2n over n to the n. So it's helpful if you rewrite the nth root. As a matter of fact, I don't often actually write it as an nth root like I have written down here. I usually just write it so I can rewrite an nth root as a power, right? So it would be to the power 1 over n. So we have e to the 2n over n to the n. So rather than write it as the nth root, I just write the power of 1 over n. I'll move this up a little bit. So I could distribute that 1 over n. So this is going to become the limit as n goes to infinity of e to the 2n times 1 over n divided by n to the n times 1 over n. So this is going to become the limit as n approaches infinity of e squared over n. Now, e squared is a number, right? It's not, when I go to plug in infinity, nothing's getting plugged into infinity there. So the only place that we are actually plugging something in is in the denominator here. So we have some number, e squared, divided by something super, super, super huge. So this whole thing is going to go to 0, and 0 is less than 1, so it converges. Questions?
Why did you go from the limit of n to infinity of the last part? how did you go from the top part to the bottom part?
How'd I go from the top part to the bottom part? So from like here to here?
Yes.
Okay. So I just multiplied, right? So 2 times n times 1 over n. This n and this n would cancel each other out, and I just get 2. And then same thing here. This n cancels out that n, and so I just get like n to the first. Does that help?
Yes, thank you.
No problem. Other questions? No? Okay. I have one more root test problem. Like I said, the root test, you don't use it a ton of times, use it some of the time. So, B, summation n equals 1 to infinity of 1 over n minus 1 over n squared, all raised to the nth power. So again, all of my stuff is raised to the nth power, so I might as well try the the root test. So this is going to be the limit as n approaches infinity of the absolute value, so parentheses, this stuff, 1 over n minus 1 over n squared to the n, all raised to the 1 over n power. So that's that, taking the nth root. And 1 over n minus 1 over n squared, as n gets really big, that's going to be positive, so I don't need to worry about it. So in this case, this is just equal to the limit as n approaches infinity of 1 over n minus 1 over n squared to the n to the 1 over n. And so just like kind of on the last problem, this n and this n on the bottom would cancel each other out. And so we get the limit as n approaches infinity of 1 over n minus 1 over n squared. And so if I plug in 1 over n as n gets really big, that first piece goes to 0, minus, again, plug in n as n gets really big, that second piece goes to 0. So 0 minus 0 is 0, and 0 is less than 1. So this is going to converge. Questions? No? Okay, so that's the ratio and the root test. So they're not too bad. Most people like the ratio and the root test the best out of all the tests, which is good since we end up using that a fair amount. So the next test that we're going to do is the we're going to do what's called the alternating series test. And so that's the last test we're going to do before break. So this is coming from section 11.6. So it's going to be alternating series and absolute and conditional convergence. So we're going to focus on the alternating series test today. After break, we'll talk about the absolute and conditional convergence. So basically, what's happening in absolute and conditional convergence is up until this point, we've just been saying every single series either converges or diverges. And so technically the series that we have been showing that converged, they were what's called absolute convergence. So the series always converges. There are some times where the series could potentially converge some of the time. But if you were to look at the absolute value of the series and figure out if that converged, it wouldn't. And so that's called conditional convergence. So basically there's just levels to converging. So we're going to look at those levels, but we're going to do that after break, not today. So today we're just going to focus on the last test that we have to learn, which is the alternating series test. So, first is to talk about what is an alternating series. So, alternating series is a series whose terms alternate positively and negatively. And you might be saying, wait, isn't that what you said the telescoping series is, where the terms alternate positively and negatively? Yeah, telescoping series, though, is a little bit even more than an alternating series. And telescoping series, remember, stuff cancels out. Right? That's kind of what the telescoping part is. You know, stuff from one term is canceling out stuff from the next term. That's not happening in an alternating series. An alternating series is just strictly, you know, any sort of thing can be happening, but it's just going to flip-flop between positive and negative. So, you know, here's a couple examples. The summation n equals 1 to infinity of negative 1 to the n plus 1 over 3 to the n minus 1. If you began to plug in values, so if I plugged in n equals 1 in here, I would have negative 1 to the first, or to the second power. So we'd have negative 1 to the second over 3 to the 1 minus 1. So this would end up being a positive 1 on the top, 3 to the 0, which is also 1 on the bottom. So its first term would just be 1. Then you'd have plus, if I plug in n equals 2, I would have negative 1 to the 2 plus 1 divided by 3 to the 2 minus 1. So we'd have plus negative 1 over 3. And so we could really write this as 1 minus 1/3. And if you kept going, right, so if you kept figuring out what these all are, you'd have 1 minus 1/3 plus 1/9 minus 1 over 27 plus 1 over 81 minus ... So we keep switching back and forth. Positive, negative, positive, negative. They could switch the other way too. You could start with a negative and then go to a positive. So it could be negative, then positive, negative, then positive. Either one works and is appropriate in terms of an alternating series. And so what we're interested in is, when do alternating series converge? So we have the alternating series test. And what the alternating series test says, you have the summation, n equals 1 to infinity. They have negative 1 to the n plus 1. It would work even if you have negative 1 just to the n power, as long as you have that negative 1 to some power where it's going to start flip-flopping back and forth. So once it's positive, once it's negative, once it's positive, once it's negative. So we have negative 1 to the n plus 1, a sub n, converges if. Okay, so there's 3 conditions. If all 3 conditions are met, it converges. Any one of the conditions fails, it diverges. So the first condition is that the a sub n's are positive. Okay, so you have this negative piece, but the negative is really being controlled by the negative 1 to the n plus 1 part. So it's really just flip-flopping back and forth, and if I got rid of that flip-flopping part, everything I have left would be positive. The second is that a sub n is greater than or equal to a sub n plus 1. So it's decreasing, right? It's decreasing terms. So we have to be a little careful in that we used to say that like we were saying decreasing for a function, so it makes sense when we say, oh, a function's decreasing. Here we're saying the terms are decreasing. As we go into each of the terms, they're getting smaller and smaller. And then finally, the limit as n approaches infinity of a sub n turns out to be 0. As long as your alternating series satisfies these 3 conditions, then it converges. Any one of the conditions fails, then it diverges. Questions? And you don't have to check them all. If you're checking them and the second condition doesn't work, you can just say at that point, oh, it diverges. You don't even have to check the third condition. So I'll give you guys a minute to finish writing that down, and then we'll put it into action. We'll try out some problems. All right, does anybody need me to wait before I go to the next page? No? Okay, so determine if the following converge or diverge. A, summation n equals 1 to infinity of n divided by -2 to the n minus 1. Okay, so you might go, well, wait a minute, where's your -1 piece, right? So it doesn't look like I have a -1 piece, but I really do. That bottom is -2 to the n minus 1, and so I could rewrite this as the following. N over -1 to the n minus 1 times 2 to the n minus 1. And remember, a -1, you can put a -1 in the top, in the bottom of a fraction, out in front of the fraction. So I could really write this as n equals 1 to infinity of -1 to the n minus 1 times n over 2 to the n minus 1. So all I've done is rewrite some stuff to kind of get it looking a little bit more like an alternating series. Questions on any of the stuff I did there? No? Okay. So then we're going to check the pieces. So we're doing the alternating series test. The first thing I have to check is that is n over 2 to the n minus 1 positive? So what do we think? Is n over 2 to the n minus 1, is that going to be a positive number? Yeah. Yep. So yeah, remember we're dealing with n's that are bigger than 1. So it could be negative, but to get negative, you're going to have to let the n be negative, and that's not happening for us. So remember, we're talking about n's that are bigger than 1. So yeah, it's positive. The second thing we want to know is is a sub n greater than or equal to a sub n plus 1. So is n over 2 to the n minus 1, is that bigger than or equal to n plus 1 over 2 to the n plus 1 minus 1? So basically I'm trying to determine do these things go down in size, right? So if I kind of clean this up a little bit, I have n over 2 to the n minus 1. Is that going to be bigger than or equal to n plus 1 over 2 to the n? Okay, so yeah. So it is, all right, and remember you have a couple choices. One of the choices you could do is you could graph. You could look at it as if it was a function. So you could graph n over 2 to the n minus 1 and see if it's a decreasing function. You can reason it out. So if you're able to be like, yeah, I believe it. I can see how that works. The other thing you could do is you could also do my cross multiplying thing, right? So you could say, all right, well, is n times 2 to the n, is that actually going to be greater than or equal to 2 to the n minus 1 times n plus 1? So is n 2 to the n bigger than or equal to n 2 to the n minus 1 plus 2 to the n minus 1? And then at that point, you might be able to say, yeah, I believe so, right? You might also be able to be like, I'm not completely sure, and then keep doing algebra. So you're going to basically do algebra till you get to a point where you are like, yes, I know that this is, bigger or not. But this is, in fact, bigger. And then the third thing we have to do is we have to check the limit as n approaches infinity of n over 2 to the n minus 1. And again, if I do that limit, I'm going to have infinity over infinity. So I'm going to have to use L'Hopital's rule. And what's the derivative of n? Mm-hmm, 1. And then the derivative of 2 to the n minus 1. So it's going to be 2 to whatever that power is. So 2 to the n minus 1 times the natural log of 2, right? So it's kind of times technically the derivative of n minus 1, but the derivative of n minus 1 is 1. And so if you take this limit, you end up with 1 over infinity, which is 0. So it converges by the alternating series test.
I had a question.
Mm-hmm.
So, in the very first step, when you were when you changed the -2 to the -1 and -1,
Mm-hmm.
How did it go up there, and why did you not include it in the limit?
Okay, so how it went up there kind of comes from basically if you think about if I have the fraction, if I had the fraction minus 1/2, right? I could write it as minus 1/2 like that. I could put the minus out in front as 1/2, or I could put the negative down in the bottom as 1 over -2, right? It doesn't matter where I put the negative in terms of a fraction. So it's the same thing here. So this -1 to the n minus 1, all this is if you think about trying to put stuff in, all this is ever going to be is a positive 1 or a negative 1. So when I put in odd ends, so like if I put in 1 or 3 or 5 or 7 and so forth, this is just going to end up being a positive 1. And if I put in an even end, like 2 or 4 or 6 or 8, this n minus 1 would turn out to be a negative, or turn out to be an odd number, and then you'd have -1 to an odd power, which would still give you a -1. So this -1 to the n minus 1, the only thing that is happening there is this is basically spitting out a positive 1 or a -1. So it doesn't matter where I put it. I could put it on the top, I could put it on the bottom, like where it started, or I could put it out in front, which is what I did here. So does that help in terms of the negative part?
Yeah, that makes a lot of sense.
Okay, so in terms of the limit, the reason I didn't include the -1 in the limit is, so this part here, this is my a sub n. And so all of the things that you do in terms of the alternating series tests are all just on the a sub n. So you figure out, is a sub n positive? Is a sub n bigger than or equal to a sub n plus 1? And we also find is the limit as n approaches infinity of a sub n equal to 0. So everything we're doing in terms of the limit only has to do with the a sub n, not that -1 part.
Thank you so much.
No problem. Any other questions? No? So B, the summation n equals 1 to infinity of -1 to the n plus 1 times n plus 1 all over n. So again, the a sub n, or the -1 to the n plus 1, that's indicating you have this alternating series. So we're going to try using the alternating series test. And we're looking at our a sub n in this case is n plus 1 over n. Right, that's what's left if you get rid of that -1 to the n plus 1 part. So first is n plus 1 over n, is that positive? Yeah. And then secondly is a sub n bigger than or equal to a sub n minus, or a sub n plus 1. So a sub n is n plus 1 over n. And I want to know, is that bigger than or equal to n plus 1 over n plus 1? So what do we think? Yes, it's bigger. No, it's not. I mean, you have a 50-50 chance of being right, right? Okay. So, not. So let's try. Let's see what happens. So again, that's not for me. That's probably somebody that did not fill out their calendar correctly. So yeah, okay, yeah. So looking on Desmos, it's totally appropriate. You can stick n plus 1 over n in Desmos and see whether it looks like it's an increasing function or decreasing function. So you can definitely do that. Otherwise, if you're going to do it out by hand, the way to do it is to look at that cross multiplication. So that cross multiplication here would say, oh, n plus 1 times n plus 1, is that going to be greater than or equal to n times, I should have really done this out, but this top part here is really n plus 2, right? It's n plus 1 plus 1. So n times n plus 2. So if we do this here, we're looking at n squared plus 2n plus 2. Is that going to be greater than or equal to n squared plus 2n? So what do we think? Is n squared plus 2n plus 2 greater than or equal to n squared plus 2n? Yeah. So, so again, right, series is kind of that first place where like your intuition sometimes in math just doesn't lead you down the correct path. So that's why you definitely want to check it out. Okay. And again, you could for sure stick it into Desmos, stick it into a graphing calculator, or work out the algebra like I did here. So yes, this is in fact less than. So now the third thing we're going to do is we're going to look at the limit. So we're looking at the limit as n approaches infinity of n plus 1 over n. And if I do that limit, I end up with infinity over infinity So we do L'Hopital's rule. We get the limit as n approaches infinity of 1 over 1. So that whole limit ends up being equal to 1. So remember, we need the limit to be equal to 0. So 1 is not equal to 0. So it fails that part, so it diverges. Questions? No? Okay. It's not too terrible. I have one more example. Is everyone okay if I go to the next page? Anybody need me to wait? No. So C, summation n equals 1 to infinity of negative 1 to the n plus 1 over n. So again, we're going to use the alternating series. Here, a sub n is equal to 1 over n. So the first thing is 1 over n positive. What do we think? Yeah, it's positive. The second thing, so is a sub n bigger than or equal to a sub n plus 1. So is 1 over n bigger than or equal to 1 over n plus 1. What do we think? Yes? No? I don't know. It's okay. Desmo says yes. So yeah. So think about it. I have two fractions, right? The tops are the same in the two fractions. The tops are both 1. The bottom, this bottom here is smaller than this bottom here. So I start dividing by bigger and bigger numbers. So think about it. Like if you compare 1/2 and 1/3, 1/2 is going to be the bigger thing. So the smaller the bottom of a fraction where the top is 1, the bigger the number is going to be. Again, if you weren't sure and you didn't want to put it into decimals, you can always do that cross multiplication. So we're multiplying this way, right? And then multiplying this way. So is n plus 1 greater than or equal to n? And then hopefully people are like, oh, well, yeah, that makes sense, right? N plus 1 is definitely a bigger number than n. So it's positive, it's decreasing, and now that third thing, we want to look at the limit as n approaches infinity of 1 over n. So what is the limit as n approaches infinity of 1 over n? Yeah, it's 0. And so that works, right? We needed it to turn out to be 0. So this converges. This series actually has a special name. So remember, we talked about the series 1 over n. So kind of like a little bit of a recall. The series n equals 1 to infinity of 1 over n, that was called the harmonic series. And we said how that was a p-series and that it diverged. The summation n equals 1 to infinity of negative 1 to the n plus 1 over n. This is actually what's called the alternating harmonic series. And as we just found, it converges. So the harmonic series and the alternating harmonic series tend to show up actually like just in math and in physics and stuff like that a lot. And so they kind of get their own name. So harmonic series, which diverges, or the alternating harmonic series, which ends up converging. Questions? No. Okay. So that's the end of the alternating series. We are going to do the conditional convergence, absolute convergence next class. So the first class when we come back from spring break. If you go and you look at the homework for section 11.6, it's in 2 chunks. And so the first chunk just asks you, does it converge or diverge? And so you could do that first section. The second section asks you about, do the following series converge absolutely, conditionally, or diverge? That's the stuff we're going to do after break. So if you wanted to look at that beginning couple of problems, you could. I think the beginning is 4 problems. So, but that gives you also some time to get like caught up on homework. It gives me time to get caught up on grading homework over a break. That's my goal for our class. And potentially to just type up all the rest of the homeworks for the whole rest of the semester. We'll see whether that happens or not. But yeah, so questions before we end. No problem. Alrighty, well, you get out a little bit early for spring break. Enjoy your spring break. Be safe. Oh, sure. Yeah. So I was going to say, you can ask your question, and then if anyone wants to stick around and hear the answer to the question, otherwise you're free to go. But sure, go for it. Which problem? C. Okay. Let me go find the problem. So 11.2 homework. Oops. Like, so this problem, the summation n equals 1 to infinity of 1 over square root of n minus 1 over square root of n minus 1, that problem? Okay, so this is one of those telescoping series. And for me, to see the telescoping series, I actually start picking n values and plugging them in. So we start with n equals 1. So I'm going to plug in and see what happens on n equals 1, what happens on n equals 2. We'll even maybe do n equals 3, and then we'll go plus ... and then we'll write down the nth term there. So for n equals 1, if I plug in, I get 1 over the square root of 1 minus 1 over the square root of 1 minus, this should have been n equals 2. I should have fixed that. So let me, 2, 3, 4, and so forth. So erase this because n equals 1 is bad. So this would be 1 over square root of 2 minus 1 over the square root of 2 minus 1. Are you okay with that? Like plugging in n equals 2? Okay. So then if I plug in n equals 3, I have 1 over the square root of 3 minus 1 over the square root of 3 minus 1. If I plug in n equals 4, I have 1 over the square root of 4 minus 1 over the square root of 4 minus 1. Dot, dot, dot. And keeps going, right? Are you okay with that? Okay. So if you think about the nth partial sum, call it f sub n, it's going to be 1 over square root of 2 minus 1 over square root of 1, right? So I'm just figuring out 2 minus 1 is 1. So I have 1 over square root of 1. Plus 1 over square root of 3 minus 1 over square root of 2. Plus 1 over square root of 4 minus 1 over square root of 3. Plus, and we keep going up to this 1 over square root of n minus 1 over square root of n minus 1. So I just basically cleaned up what I had a little bit and then put that nth piece in there. Does that make sense? Okay, so now I begin to look, and this is where I get the formula by cluing into what is canceling. So if you look, this piece here cancels with this piece here, right? The positive, so the first piece in a parenthesis cancels with the last piece of the next parenthesis. So that first one cancels out this one. Does that make sense? Yeah, so then this piece here, the 1 over square root of 3, that cancels out with this piece here. So this piece cancels out this piece. Now I can't see the next term. I didn't write the next term. I didn't write n equals 5 down. But what would happen is this piece here would cancel out with the second piece in this next parenthesis over here, right? And this would keep going. So if you notice, the second piece of a parenthesis is always getting canceled out by the previous thing, right? So like this second piece of the parenthesis was canceled out from the previous one. This second piece of the parenthesis was canceled out from the previous one. This second piece of parenthesis, which I can't see, is canceled out by the previous one. So when I get all the way out to the end, the previous term here is going to cancel out the second piece of the parenthesis here. And so what I'm left with is just the minus 1 over square root of 1 plus 1 over square root of n. So I'm just left with negative 1 plus 1 over the square root of n. And then I take the limit of that. So we look at the limit as n approaches infinity of negative 1 plus 1 over the square root of n. And that ends up being negative 1 plus 0, or negative 1. Does that help? The notes from last class? Let me see what I put as the solution. Let me see. Oh, it's because in the solution, which maybe I just wrote the problem down incorrectly from the beginning. Let me look at the problem again. Oops. Oh no, it's because in the solutions I actually write the wrong problem. So in the solution, I actually made this here a plus instead of a minus. So that's why we got something wrong. That's why it differs. So basically my solution for C is not correct. No problem, anytime. Anybody else have any questions?
Thank you, Professor. Have a nice day.
No problem, you too.